So the final question is about a manometer that's filled with mercury and it measures atmospheric pressure. So a column of liquid mercury is held up by the pressure of the atmosphere acting on the liquid mercury. Figure 9.1 shows a manometer under pressure of 101 kilopascals and the height of the liquid mercury is 760 millimeters. So this would be a vacuum up there, and the reason that the rest of the thermometer mercury doesn't come out of the manometer is because the air pressure is pushing it and forcing it back up. Now we've got to show that the density of liquid mercury is approximately 1.35 times 10 to the 4 kilograms per meter cubed. So what we know, let's get my blue pen, is that I know that the pressure is equal to the density times G times H, and if I rearrange that for density, that will give me the density is equal to the pressure divided by G divided by H, and I've just got to be a bit careful with my units because I'm in millimeters up here and I'm in kilopascals for the pressure, and I need to be in SI, kilograms, meters to the minus 3. So let's put my numbers in. So the density is going to equal the pressure, which is 101 times 10 to the 3 pascals divided by 9.81 multiplied by the height, which is 0.76. And when you tap that into your calculator, that should give you an answer approximately 1.35 times 10 to the 4. So part B, we've got to state Archimedes Principle, and that states that the upthrust is equal to the weight of the displaced fluid or liquid. And what we've now got to deal with is a steel cuboid of volume 35.0 centimeters cubed is fully submerged through into a trough of liquid mercury. Calculate the initial upwards acceleration of the steel, when we've got the density of steel being 7,850 kilograms per meter cubed. So if we just draw a diagram, we've got a trough of mercury, we've got some steel in there, and the first thing we need to know is, well, we've got two forces acting on the steel. We've got the weight of the steel and we've got the upthrust, and because it says it's going to accelerate upwards, the upthrust is going to be greater than the weight, because it's just the initial acceleration, we haven't got any drag forces involved. So let's work out the weight of the steel. So in order to work the weight of the steel, first of all we need to get the mass, and the mass, well, the density of an object is the mass over the volume, so the mass is going to equal the density of the object multiplied by the volume. Again, I've got to be careful with my units here. So the density is equal to 7,850, and I need to multiply that by my volume, but that needs to be in meters cubed, and there are 10 to the 6 or a million centimeters cubed in a meter cubed, so I need to go 35 times 10 to the minus 6 meters cubed, and then if I multiply that by G, that gives me my weight, so that's going to be 7,850 times 35 times 10 to the minus 6 times 9.81. Now the upthrust is equal to the weight of the fluid displaced, so the upthrust is going to equal the mass of the mercury that's been displaced, and so that's going to be 335 times 10 to the minus 6. This is the volume multiplied by the density, which was given as 1.35 times 10 to the 4. And then if we multiply that by G, we get our upthrust. Now we're going to have to go back to F equals ma, and again the F is the resultant force. So my acceleration is going to equal my resultant force divided by the mass of the steel. So that's going to give me 35 times 10 to the minus 6 times 1.35 times 10 to the 4 times 9.81 minus 7,850 times 35 times 10 to the minus 6 times 9.81. And I subtract those two together. If I then divide them by the mass of the steel, which is going to equal that, 7,850 times 35 times 10 to the minus 6, that will give me an initial acceleration of 7.06 meters per second squared.